Hey everybody, in this video we're going to do another method of initial rates problem, this time focusing on whole numbers and what can be a whole number, what cannot be a whole number, to see how this process can look a little bit more complicated but still be pretty much the same thing. Here I have 3 experiments. The goal is the same as always. We want to compare any 2 experiments where only one reactant's concentration changes. For example, if we compare experiments 1 and 2, you'll notice that B stays the same. Only the concentration of A is changing, and that's what you want to find. In this case, A's concentration goes up not by 1 or not by 2, but by a decimal, by 1.5. And that's kind of the point of this entire example, is just to say that that is okay. You're allowed to see non-whole number or decimal changes between the concentrations. Next up, we'll do what we always do and look at the rates of those reactions to see how they change. And the initial rate also goes up by the exact same amount, 1.5 times faster. You can use the same mathematical trick as always. 1.5 to what power gives you 1.5. Of course, that's going to be the first power, or an exponent of 1. Or you could just notice without doing the math that the molarity and the rate change by the same quantity, so that is sort of the definition of what it means to be first order. We can now start putting together that rate law as soon as we have some of those orders. So rate equals lowercase k, and A has an order of 1. Okay, so next up we need to find the order of reactant B. That means I need to find 2 experiments where only B's concentration changes. Obviously in 2 and 3, A stays the same, and then B changes by some factor. And it's not a super obvious one, so you can always divide those. 0.272 divided by 0.16 to find out exactly what that change is. And in this case, it looks like it is 1.7 times higher in experiment 3. We'll check the rate now to see how much, how many times faster the rate is in experiment 3. Again, I can't see that just by looking at these numbers. I have to divide them out. And here I find out that the rate in experiment 3 is 2.89 times higher. So you just got to remember what we saw with reactant A. You are allowed to have decimal changes, even strange ones like 1.7 and 2.89. The same mathematical trick we always use is going to get you home here. 1.7 to what power will give me 2.89. Let's be clear about this. The orders that you will see, the exponents, those will almost always be whole numbers. At higher levels you might see non-whole number orders, but in your standard chemistry class, the orders will either be 0 or 1 or 2, maybe every once in a while 3. And what that means is you can just kind of test what exponent is going to solve this equation. 1.7 to the 0th power, it's not going to give you 2.89. 1.7 to the first power would be 1.7, so it's not that. 1.7 to the second power, if you plug that into your calculator, you'll see that it is actually 2.89. So sometimes you can have some very strange looking changes like 1.7 and 2.89, but the orders themselves should always come out to nice whole numbers like 0, 1, or 2. So now I have the whole rate law. I can say that the reaction order is 1 plus 2 equals 3, so this would be a third order reaction. And now I can do some of the math to determine the value of K with the units. Remember, we're going to choose any experiment. I always go with experiment 1, and we're just going to plug in all the numbers we see there, like 2.24 times 10 to the minus 3 gets plugged in for the rate. Concentration of A here in experiment 1 is 0.05 and B is 0.16. Don't forget to square it because B has an order of 2, and then just do the algebra to solve for the value of K. And when you do that, this K value comes out to 1.75. We also need to get the units on K, because remember, the units on K are different depending on this total reaction order, this third order thing. If you don't know what the third order K units are, you can do that math again, but this time, instead of plugging in the number for what the rate is, plug in the units on rate, moles over liters times seconds. The concentration of A, of course, like any concentration, moles over liters, and B would be moles over liters squared. If we start simplifying this down, over here on the right hand side, multiplying all those moles over liters together, I get moles cubed over liters cubed, and I didn't touch the left hand side yet, so that's still moles over liters times seconds. To cancel out the fraction over here, I'm going to multiply both sides by the reciprocal. liters cubed over moles cubed. That's going to cancel this, leave me with K equals, and if I simplify this down, the liters cancel, leaving a liters squared on top, and the moles cancel, leaving a moles squared on the bottom. I'm going to come over here and apply those units to my K value, liters squared over moles squared times seconds. And that's the whole problem. That also wraps it up for this video. Thanks a lot for watching.